Question 14. Question 14 says, light of wavelength 600 nanometers falls on a soap bubble of thickness T. How thick should the bubble be for destructive interference? This kind of problem has a lot of pitfalls, so one has to read it very carefully a couple times, make sure they understand it. So again, light of wavelength 600 nanometers falls on a soap bubble. How thick should the bubble be for destructive interference, not constructive, right? This is the topic of what's known as thin film interference, right? So we have the soap bubble, looks like this. And then the light is coming in. So here's what we have to analyze. The index of refraction of air is 1. What's the index of refraction of the soap bubble? It's given here as 1.5. N is 1.5. So when the light hits a medium, it does two things. One part of the light reflects from that medium. The other part of the light transmits into that medium. So this is called reflection, transmission, right? So part of it reflects, okay? The other part of it refracts, transmits into that medium, right? So it goes into that medium. So now, how about this interface? This is also air. So part of it will transmit into the air, so it will bend outward from the normal. So we're going to come like this, bend towards the normal, bend outward away from the normal. And at this interface, part of it will also reflect, right? So reflection, okay, when it hits this medium, part of it will also reflect, part of it will transmit, right? So what we're looking at when we're analyzing thin film interference is the interference of these two waves. The one that reflected immediately from the top of the surface, and the one that reflected after transmitting, the one that reflected and transmitted. Okay, other things of course will happen. This one will go through, it will bounce back, transmit, and then it'll go through, it will bounce back, it will go like this, it'll transmit, and so on. But the intensity of those waves is much, much dimmer than the original two waves. So we want to see the interference of these two waves. Let's say our eye is here. How are we going to see those waves? Okay, so here's what we're going to conclude. The first reflection that happens from a lighter medium to a heavier medium, the theory of physics says when a wave reflects from a lighter medium and hitting a heavier medium, upon reflection there's a 180-degree phase change, pi radians, right? So over here, there's a 180-degree phase shift from lighter, medium, to heavier medium. From a reflection from a lighter medium to a heavier medium, right? So another way to say that is that's a phase shift of half a wavelength, right? A complete wavelength is 360 degrees, half a wavelength is 180 degrees. So lambda over 2, okay? Then the transmitted wave goes, reflects back. So upon this reflection, is there a phase shift? Well, this is a heavier medium, this is a lighter medium. From a reflection from a heavier to a lighter, there is no phase shift, okay? So no phase shift, from heavier to lighter. Okay? So therefore, you have basically one phase shift here, no phase shift there. And then this one goes here from a heavier to a lighter, and then it transmits. There's no phase shift upon transmission, okay? Upon transmissions, there are no phase shifts at all. They just transmit as they came in. So these two waves, out of these two waves, one of them has already experienced a 180-degree phase shift, right? So what is the condition for constructive interference, right? Constructive interference. Constructive. Okay? Since one of them has already experienced a phase shift of lambda over 2, what we want is the path difference that the second wave took an extra path, right? What was the extra path that the second took? T, 2T, right? So it's double the thickness. The thickness of the soap bubble is T. So the extra path that the second wave took is 2T, right? So we want the 2T, double the length. We want it to be n plus half of the wavelength of the wave in the medium. In medium. Okay? So basically here is the argument. This one is going to be n is equal to 0, 1, 3, 5, 7, 9, and so on, right? So if the extra path is experiencing half a wavelength, then you have an extra distance that this one is traveling. This extra distance is 2t. If this extra distance that this one is traveling is half a wavelength multiple of the wavelength of the light wave in this medium, right? The wavelength of the light wave in the medium. So the logic behind it is this. Since this guy is already out of phase from this wave, right? We can make this in a different color. Okay, so the black one is already out of phase from the blue one by 180 degrees. So if the blue one travels an extra path such that that extra path is an integer multiple of its own wavelength, then it will come back to the top out of phase from the original one by a complete wavelength, right? Because this one is already out of phase from this with half a wavelength, right? By half a wavelength. So if this travels another half a wavelength more, or 3/2 wavelength, or 5/2 wavelength, then basically by the time that they meet here, there's going to be constructive interference, right? So this is going to be 2t is equal to n plus half lambda. Now the wavelength of the wave in the medium is what? Well, we learned earlier that when a light wave goes through a medium, its wavelength decreases by a factor of n, right? So we put here lambda over n, okay? So this is the wavelength in the medium, and then the n goes over here. 2tn is equal to n plus half lambda. Now, in order to not confuse between these, because you see here, this is the index of refraction, and this is the integer multiple. So let's use a different symbol. I'm going to use m here. m, okay? m is equal to 0, 1, 2, 3, 4, 5. Okay? So we'll just make this m. Therefore, you will not confuse it with the n, the index of refraction. Okay? Now, this is true. So 2tn is n plus half lambda. It's true for constructive interference. Okay? How about destructive? Well, our argument is going to be if 2t is equal to integer multiple of the wavelength, 2tn is equal to integer multiple of the wavelength. So let's make this also m. Then what's going to happen? Okay, so let's make 2t is equal to m lambda in medium. So if the extra length that the second wave traveled happens to be an integer multiple of its own wavelength, when it comes back to here, it's got to be out of phase with the original one by how much? By half a wavelength, and you're going to have destructive interference. So this one is going to be destructive. So then this one, you're going to have what? You can have m is equal to 1. You can have m is 2, m is 3, m is 4. So you can have m is 1, 2, 3, 4, 5, so on, so on. Integer multiple of wavelength. This is integer multiple of half a wavelength, right? So in order to answer this, then we want it to be destructive interference. So what are we going to do? We're going to put 2 times the thickness is going to be what? Well, we don't know the thickness. The index of refraction, 1.5. We're going to put here m is 1. And then the wavelength. The wavelength actually is 600 nanometer. Okay, so this is going to be 3t is equal to 600. T is equal to 200 nanometer. So the answer is D. Now, what if it had said something like this? A light up wavelength 600 nanometers falls on a, let's say instead of a soap bubble, it's a layer of soap on the ground. So, layer of soap. On ground. Okay? So now how would that change the answer? Let's say it said how thick should the bubble be for destructive interference again. So in this case, what ends up happening? Well, now you have index of refraction of 1, index of refraction of 1.5, and basically here the light doesn't do much penetrating in the ground because it's a very heavy medium, right? So now you have the light wave comes, bounces, you have it changes by half a wavelength, then it transmits, it bounces. Okay, now how about here? From hitting from the soap bubble, right? Instead of a bubble, now it's a layer of soap, right? Or you can say layer of oil or something, right? And then this is the ground. Upon reflection from the ground, there's also going to be another half a wavelength, right? So both of them are going to reflect and change their angles and be out of phase by pi radians, right? So half a wavelength, half a wavelength. So then, what's going to be the condition for constructive? What's going to be the condition for destructive? In this case, constructive is going to be 2t is equal to m lambda in medium. If the extra path traveled by the one in the soap layer is equal to integer multiple of wavelength, then that's constructive interference. So this is going to be, again, 2t is equal to m lambda over n, and then n goes over there. 2tn is m lambda. And then this one basically gives you m is 1, 2, 3, 4. Now notice what happened. This is this time constructive. It's the same equation as for the other one, destructive. And then the opposite happens. For destructive, you have 2tn is equal to m plus half lambda. Same equation as that one. And then m is going to equal 0, 1, 2, 3, so on, so on. And that's going to be destructive. So what would the answer be this time? And you would put here 0 because we were asked for the destructive. So you put here 0, half a wavelength. Then you have 2 times t times 1.5. And then the wavelength is 600. 600 over 2 is 300. And then the thickness would have to be what? Well, that's 3. 300 divided by 3, 100. Okay? And actually, that's one of the answers. 100 nanometers is one of the answers. So in that case, if it was a layer of soap, it would have to be 100 nanometers only. But if it's a soap bubble, it would have to be 200 nanometers, right? So read the problem carefully and analyze it. The other thing you should not forget, another pitfall here, is that some people might forget the index of refraction, the n, right? So if you forget that, you have to take into account the index of refraction of the medium, you're going to get a much different answer for the t, right? So you have to include that index of refraction in your problem, right? Okay, so our answer for this one is D because it is actually a soap bubble with air in the middle, okay? Thank you very much.